Okay, so 3.5, so graphs of relations and functions. So really more graph stuff. We're just kind of deepening our understanding of this stuff. Yeah, so relation versus functions revisited. So remember, what was our definition of a function? You guys remember that in that lesson there? Yeah, one value of x for every value of y there, right? So another way of showing that with a graph, right, is something called, maybe I'm getting ahead of myself here. We could do something called a vertical line test. You know what? No, let's, yeah. Well, like in this example, this one would be a function because for any value, let's say like x is like, 1 here. Well, then there's one value of y for that one. For, 2, there'd be one value of y. But like look in this one. Like if I had 1, right, so a value of 1 right there, then there's actually 2 different values for that one value of x. So quite often, we'll do something called the vertical line test. So if you end up drawing lines down this thing and it crosses in 2 places, then that's not a function. Yeah. Okay. So yeah, let's move on. We were just kind of doing that one. Yeah, that's kind of what we had going on there with the vertical line test. Okay, now discrete versus continuous data. So this is really getting at when do we connect the dots and when do we not connect the dots, right? So you see like in this graph, we have discrete data. So that's going to be like our dots, or just they stay as dots on our graph. And then continuous, we'd actually have like a line that goes forever that way and forever that way in the end. Now, just some examples here. So if I had a question where it said the number of shots that you take in a hockey game, and then your output or your y value would be the number of goals scored, do you think that that would be continuous or discrete data? Discrete, right? Because you can't shoot half of a hockey puck. You can't get half of a goal, right? So those would be a situation where you just have dots there. But then if it was something like someone's height versus their weight, right? Like your height is like on a changing scale. There's everywhere in between, and then your weight would go up, the same. So in this example here, so let's say, does each graph represent a relation, a function? How can we tell? So let's say like looking at, we'll just kind of talk about it for the sake of time here. So looking at this one, let's say like this first one here, Joe's graph. What do you think? Relation, function, how do we know?
We'll draw vertical lines and see if they can connect.
Yeah, that actually would work, right? That you could do that vertical line test. Or you can kind of see that there is no like dot over top of any other dot like there would be in that case. So this one is a function. Same with the other one actually. So which of these graphs should have the data points connected? Or sorry, let's look at the bit more examples. So in an environmental study in North America, Joe collected data on the number of different species of birds he heard or saw in a 1 hour period every 2 hours for 24 hours. Alice collected data on the temperature in the area at the end of each 2 hour period. They plotted their data. So Joe's graph is the number of species versus the time, right? So would you connect the dots in this example? No, not really, right? You're not going to connect dots in that example, right? Because that wouldn't really make any sense to have that, that as time goes by, we've got like different numbers of species kind of going on. With Alice's example, would you connect the dots? Being temperature? Yeah, that would be, because actually those would connect to each other, right? And they probably wouldn't be straight lines though either, right? They would probably in real life be like some curves that went like that, if that was what was really happening there.
So then a relation, is this called a relation graph because they all relate to each other?
Determining the domain and range of a function / relation. So up until now, domain and range, we were pretty much just listing the values, right? Like in the last lesson, we just pretty much listed our x values, right, or our inputs for our domain, listed our y values or our outputs for range. Now, in this example, we're going to be looking at a graph like this one, where we're going to say, what is our range? Like, what's our allowed values in this case? And in this situation, a closed dot, whenever we have a closed dot, will mean that we also include that point. So our x will also be that point. So closed dot, And do I have an example of an open dot?
No.
Then that's an open dot there, right? So if it was an open dot, then that would not include that point, right? Like an open circle wouldn't include it. We did this in Math 9 too, but we weren't doing it with a two-dimensional graph. Do you guys remember how we had like a number line? And if it was like, 0, 1, 2, and we'd have like an open circle and then like this way, and that would be like everything less than 2, but not including 2. It's that same principle with the open dot or the closed dot, but now it's going to apply to like a two-dimensional, like a Cartesian plane, right? So we've got like our x and our y that it'll be applying to. So if we were going to solve now for the domain of this graph here, then really what we're doing, right? We're saying what is x allowed to be. So am I allowed to have a point like out here? Like does that point exist on my graph? No. So or like this point here or anything, right? Or this point here, those are outside of the x values that are allowed. But let's say, what if we had x is equal to 2, right? So then that would be this point right here. So x is equal to 2 is an allowed value for x, so for our domain. What about x is equal to -3? Is that one allowed in our... It is, right? Because it's solid, right? It's a solid dot there, so that one's also allowed, right? That x value would have a y value of 2. But yeah, that x value is allowed. Okay, so it looks like to me that we could say that x has to be between -3 and 2, right? That's going to be our domain. It's like any number for x as long as it's between -3 and 2. You guys kind of see that? So whenever I'm saying domain, you're looking this way. You're looking at your x values. Okay? And whenever I say range, we're going to be looking up and down. We're going to be looking at our y values. So the way we would write this typically, and this is very common in pre-calculus courses, so from now on, you guys will see this all the time. So you'd say the domain, like d, ... like I did like in the last unit, or last lesson. And then we just say x has to be greater than or equal to -3. You guys are good with your greater than or equal to symbols, right? The alligator wants to eat the bigger one. Yeah, okay. And x has to be less than or equal to 2. You guys are good with that one? It's like x is sandwiched in between -3 and 2, right? It's anywhere in between those two numbers. So for the most part, when you're doing these, you can almost like write out domain is equal to, and then you could write an x, draw those two symbols, right? That's kind of getting it ready. And then it's between -3 and it's between 2.
Can that be your final answer?
Yeah, that's your domain. Technically, though, the whole thing written out in Mathanese here would be, x is greater than or equal to -3, less than or equal to -2, and then you'd write a comma and say where, a comma in math means the word where, x, and then this will be a new symbol, is a member of the real numbers.
Excuse me.
And all that's saying, that last part that's tacked on there, is saying that x can be, well, real numbers, right? Real numbers are like they're fractions, they're decimals, they're anything in between, right? So it's saying x is allowed to be like 0.5. That's allowed, right? That would give me that point right there. It's allowed to be 0.001, right? It's allowed to be that point. It's allowed to be anywhere in between. That's all that last part on the end is telling us. Okay, so that's domain, right? Same thing with range. We're just kind of looking in the other dimension here, right? So range is our y values, are up and down. So in this case, we could just write it out as range. So r ... is equal to, now I'm not going to use x, right? Because I'm asking for what y values are allowed. So we can just write it out. We could start it like this and say, okay, y has to be greater than or equal to something, and less than or equal to something. So y has got to be sandwiched in between two numbers. So what does y have to be greater than or equal to?
2.
2?
0.
Ooh, I heard something over here. No.
Wouldn't it be 0?
What?
2 and 2.
No, it won't be 2 and 2. What's the lowest point on this graph?
0.
-2, right? This exists down here, right? This is a point on my graph. That's as low as it could ever be. But it does exist. That's the bottom, right? So that y value is allowed. So it's got to be greater than or equal to -2. And it's got to be less than or equal to 2. Okay, and like I was saying before, if this would have been like an open circle instead, right? That would have been an open circle there. Then that would mean that that point isn't included, and all that would change is it would look like this. You just wouldn't have the line underneath. It would just be y is less than or equal to, or sorry, just less than 2, not less than or equal to. Okay. Like I said, big concept. This comes up a ton in pre-calculus, right? We're constantly doing stuff with domain and range, so yeah. Oh yeah, sorry, and then the last bit here. I don't really talk about that yet here, and you don't need to worry too much about it, right? This is a great answer, but just in the end, if we're being thorough, you'd write where y is a member of the real numbers, and that symbol there means is a member of. Just, you don't need to.
So we don't have to.
All right, so we'll do some examples here in a bit. So, yeah, let's skip on to question 3. So, for question 3, for each graph, does the graph describe a relation?
Yes.
Yeah, they pretty much all do, right? If we're making a graph out of it, and there's some relation between the x values and the y values, then yes, they do represent a relation. What about function? Are they both functions? Only a is a function, right? And you could do that vertical line test again, like right, if we drew lines going straight down, it only ever crosses at one point, right? But if we do that to the circle, right, if we make these lines, then for any value of x, there's multiple values of y, right? Like at 6, there's actually 2 different y values for that one value of x. So that one's not, so b is not a function.
So just a function can't have 2 values in the same line.
What's that?
A function can't be the same, otherwise like you can't have 2.
So now, given the domain and range in words, right? So let's just we'll just say it. This is an open circle. It's kind of hard to see there. I don't know if you can see it better on your end. And this is a closed circle. So let's look at our domain first. So our domain, so I'll just write D. What does x have to be greater than?
3. Negative 4. Negative 6.
Yeah, -6, yeah. Yeah, I know this one's not labeled, but this would be -5, and this would be -6 right there, right? So our x value there, right, the farthest left we're going to get with our x is at -6. So x has to be greater than or equal to -6. And then it's going to be less than what?
3.
Less than 3. And just less than because it's an open circle. Okay, so let's write that out. That would be x has to be greater than or equal to -6. And it has to be just less than 3. Okay, now this notation that we just did, this is called set notation or set builder notation. You'll see it sometimes. The other way of writing this is something called interval notation. All right, so now kind of the difference between these. Set builder notation we use quite a lot in pre-calculus, like in high school. If you guys get into like calculus or in university, they quite often I find use interval notation a lot more. Right, so you kind of need to know both. Interval notation would look like this. So, okay, so interval notation, the way this works is we'll do the same thing. So but we're gonna, it actually looks like a point. So you're gonna have like, it'll be from -6 to 3. And we don't write an x in there or anything else. But then if it's including that point, we use a square bracket on the end, which it is, right? It's x is greater than or equal to. And if it's not including the point, like in this case, then it's just going to be a round bracket. So that'd be interval notation. And the problem is it kind of looks like a point, right? And so people confuse that with a point on the graph, but that's actually, that would be the domain is equal to that. So square bracket is including the point, round bracket is not including the point. It's technically easier, I think, once you get used to it. But all right, let's do range. So what about the range on this one? So the range would be, Yeah, so we can even start it this way, right? Y is got to be, well, greater than or equal to, or just, is it greater than or greater than equal to?
Greater than.
Just greater than, right? Because this is an open circle. And it's greater than, what did you say? -4, yeah. -4. And then it's going to be less than or equal to 5. Okay, in interval notation, this would be the range is, okay, so it'll be -4 to 5 again. And then we'll just make sure we got the brackets right. So this is an open circle, so it's not including -4. So would it be a round bracket or a square bracket? Round bracket. And then this one is including 5, so it'd be square bracket.
Oh, my brain.
All right.
Yeah.
Here, you know what? I'm going to pause it. I'm going to let you guys do this one. Can you guys do it in, yeah, set builder and interval notation? And then I'll let you check your work here when you're done. Okay, so the question is, how do you know whether or not it's like greater than or equal to? You can see that if this point here, right, this really does pass right through 1. So it does include 1. You know what I mean? Like it actually, like it does start at 1 there, right? It's not like just missing 1, you know, it's not just before 1. It actually does come to 1. And then on this side too, it comes all the way to 7. So it's going to be including the greater than or equal to or less than or equal to. So, okay, yeah, so this will be x is greater than or equal to 1, less than or equal to 7. And then technically you'd have where x is a member of the real numbers. And as set builder, or sorry, interval notation, square bracket, 1, and then 7, and then square bracket, right? It's just including both. Okay, your range would be similar, but with a y. So y is greater than or equal to -3, and then 3, where y is a member of the real numbers. Another way of writing that would be -3, comma 3. Okay. The way we could write that, to get you started on this one, you'd say the domain, same thing, it'll be x is greater than or equal to something, you know, less than or equal to something. This arrow means that our x values are going to keep on going forever, right? This thing is going forever to the right, never stops. So we can say x is less than or equal to infinity. It's like a sideways 8. That looks open. Yeah, so that should just be just greater than -2. And then quite often what we do in math too is that instead, like this is right, like you could write it as less than or equal to infinity, but quite often you would just write it as just the first part there, like x is greater than -2, and that'd be fine. You're just saying x has to be greater than -2 and just kind of leaving out the infinity. Or the x could be on the other side too. X is greater than -2. Like those are all fine ways to write it. All right, let's do the range on that one. All right, y has to be greater than -3. Done. Good enough. You could write the infinity thing again, that'd be fine, or just y is greater than -3. That's also fine, right? It's just saying y has to be everything greater than that number.
Hello? Can I go to the washroom?
All right, range, or sorry, like graph B, let's say, okay, the domain of this one. Okay, first off, is it going to be greater than or equal to? This one's a closed dot and this one's an open dot. Yeah. Yeah, the equal to will kind of trump it, right? Because it is equal to it at that point. So x would be greater than or equal to, and then what would it be greater than or equal to? 0, right? Our x value there is 0. Less than or equal to 5, right? Is our last point there. Okay, and then our range would be y has to be greater than or equal to 2, right? That's our bottom. And now what would this be? Is it less than or equal to? Just less than, because it's an open circle. Less than 7. Yep.